We're happy to have Yupeng talk about efficient zero-knowledge proofs from interactive proofs.
Hello, everyone. I'm Yupeng Zhang. I just started as an assistant professor at Texas A&M University. And today I will talk about some of our recent work on constructing efficient zero-knowledge proofs from interactive proofs. And in particular, I'm referring to the doubly efficient interactive proofs, the GKR protocol. Okay. So the concept of zero-knowledge proof has already been mentioned in many of the previous talks. So very quickly, it allows a prover to convince the verifier that like a computation, for example, modeled as a circuit on a public input X and a secret witness W, and the output is Y together with the proof. Okay, and then we have completeness, soundness, and zero knowledge defined like in this way. Everybody's clear with the definition? Yeah. And in zero-knowledge proof, we are interested in the following efficiency measures, right? We have a prover time, proof size, and verification time. And for those constructions where the proof size is smaller than the computation or a circuit, we call it the succinct zero-knowledge proofs. And here, we also allow the verifier to interact with the prover, which is not like illustrated on the slide. And actually, our constructions are interactive, and we can make it non-interactive using field-Shamir random outcome model. Okay. So since it was introduced in the early days, there are so many fancy constructions of zero-knowledge proofs, and actually Riyad gave a very good survey about it. And since he's not here today, I'm just going to steal his slide to make sure that I don't miss anyone's work. You can see those fancy constructions, and here's the. Well, oh, yeah, I don't have my slides. It's, no, that's how it is. Here's the reference. Yeah. And going back to my own slide. So I guess the most widely deployed ones in practice now is like based on snarks. So from early constructions of Groth and Lipma to the like QAP-based ones introduced in GKR. Later, there's a Pinocchio implementation. There's a whole series of improvements on the functionalities, efficiencies, and so on and so forth. And recently, we have Sonic making an updatable and universal common like structure reference string. And one of the reason it is like the most widely deployed one is it generates a constant size proof, and in practice, only like hundreds bytes, and the verification is super fast. So this is great for applications like blockchain. But there are two disadvantages of snarks. The first one is trusted setup. It requires a structured reference string with a trapdoor, and you cannot leak a trapdoor, and otherwise there's no security guarantee. Okay? And the second one is the prover time is relatively slow because it requires public key operations, in particular multi-scalar exponentiation, which is the size linear to the size of the circuit. Okay. And to address these issues, more recently there are many constructions and efficient implemented systems. And here's a short list categorized by their underlying technique. Okay. And again, this is just a small subset, and I'm mainly referring to those with implementations recently. And there are many work before these things to like on the foundation of these techniques, and also recently there's a lattice-based succinct zero-knowledge proof which was presented yesterday. And my research is mainly focusing on this line of work, constructing efficient zero-knowledge proofs on the so-called interactive proof. Okay. And so today I'm going to present some of our recent progress along this line, and just to like give some features ahead of time. So systems building on interactive proofs usually have a fast prover time because for the main body of the protocol on the circuit, we only require like module additions and modifications, and there's no expensive public key operations like exponentiation and parity. Okay. And then the verification time can also be made succinct if your circuit has structure in it. So this was inherited from the original paper. So when your circuit is log space uniform, we can actually validate the computation faster than running it locally. Okay. And as I said, for interactive proofs, I'm particularly referring to the doubly efficient interactive proof proposed by Goldwasser, Kalai, and Rosblum in 2008. And we usually refer to it as the GKR protocol. Okay? So GKR protocol is a protocol for delegation of computation. Okay? So let's say the verifier wants to evaluate a function modeled as a circuit on input x, but she's not powerful enough to evaluate on her own. Then she can actually use this protocol to delegate the computation to the prover side and validate the results by interacting the prover. And the verification time is actually faster than computing locally if the circuit has structure. Okay, so this is the GKR protocol for delegation of computation. And actually, I'm going to present great details of GKR protocol just in the next several slides. Okay. So in this talk, I'm going to talk about 3 improvements in 2 of our recent papers. So the first one is to reduce the prover time in GKR to linear for arbitrary circuits, which is optimal. Okay. The second one is to achieve zero knowledge and turn it into an argument system and achieve zero knowledge efficiently. And the last one is a construction for transparent polynomial commitment, meaning that it's not based on bilinear pairing, there's no trusted setup in this polynomial commitment scheme. Okay? And the first 2 are in this paper we published in Crypto this year called Libra. And the third one is a follow-up work in Submission. And the system is called Virgo, because apparently the name Libra is taken by Facebook. So, and these are joint work with Tiancheng, Jiaheng, Babis, and Zhang. So to start, I'm going to talk some more details about the construction of GKR protocol. And to start with, I will present part of this Sumcheck protocol. And I actually really hope Guy can cover this in his talk on Monday, but he didn't have enough time to do that. So here I'm just going to show you some of the idea. Okay? So Sumcheck protocol is actually a very important protocol in the whole literature of IP and PCP. And the task is to compute the summation of a polynomial, multivariate polynomial f, defined over the whole field, but only on this Boolean hypercube. Okay. We want to sum up f from 0, 0, 0 all the way to 1, 1, 1. Okay. And here we are in the world of polynomial time, so the number of variables is log n, and then the size of f, or the number of monomials, is at least n, right? It's n if f is multilinear, and it's polynomial if f is larger than that. Okay. And computing the sum requires at least order of n time, simply because there are order of n possibilities of the binary string. Right? But the verifier doesn't want to compute this on her own, so she can actually delegate this computation to the prover side, and Sumcheck protocol is particularly for that purpose. So the way it works is the prover is going to send a univariate polynomial defined on the first variable to the verifier in the first round. And this equation is the formal definition of how to compute this univariate polynomial, but you don't have to remember it for the rest of the talk. But just it's roughly summing up the Boolean hypercube with one less variable. So the sum is of half of the size. Okay? And with this univariate polynomial, the verifier is going to do some verification, checking consistency between this h and this univariate polynomial f1, x1, which I'm also going to omit on the slide. Okay. After that, the verifier is going to send a random challenge to the prover called R1. And using this R1, the prover is going to send another univariate polynomial defined on x2, given by this sum, is again half of the size of the previous one. Okay? And they just do it round by round, and eventually in the last round, the prover is going to send a univariate polynomial for the last variable defined in this way. Okay? And the last step of Sumcheck, the verifier needs to check the consistency of this last univariate polynomial to the original multivariate polynomial. And the way is by computing or giving access to this multivariate polynomial evaluated at point R1 up to R log n. Okay? So that is the whole picture of Sumcheck protocol. Is it clear here? And some of the features. So as I said, if f, for example, is multilinear, that's the one we are going to use for this talk. there are exactly n monomials or n coefficients for a multilinear polynomial with log n variables. Okay? But the proof size of Sumcheck protocol is only order of log n, because there are log n rounds and the size of each univariate polynomial is constant. Okay? And verification time is also log n plus this final so-called oracle access to this evaluation of the multivariate polynomial. And we are going to explain how does she get this oracle access in the GKR protocol. So that is the Sumcheck and it's some of the efficiency measures. With that as a building block, the GKR protocol works as following. So it models computation as a layered arithmetic circuit with addition gates and multiplication gates. And the input is x at the bottom, and the output is y. Okay? So in the first step, we are going to define a multivariate polynomial or multilinear polynomial using the input x, and we call it VD. This is actually the multilinear extension, and the way you can think of it is as following, right? So if x is x0, x1, x2, and so on and so forth, we just want the evaluations of this multivariate polynomial to match the input, right? We want v000 to equal to x0, and then v001 equals to x1, and so on and so forth. Okay? So in this way, if the polynomial is multilinear, there's the input defines a unique multivariate polynomial, that there's a one-to-one mapping between the polynomial and the input. Okay. And similarly, we are going to define one polynomial using the values in each layer of the circuit. Of course, after the evaluation of the whole circuit in this way. Okay, we have a V0 up to down to VD. Okay. After that, you can observe that there is actually a relationship between the two polynomials defined by two consecutive layers, simply because they're connected by the circuit, right, by addition and multiplication. For example, here is a multiplication gate. It means the evaluation of V0 at location 0 equals to the evaluation of V1 at 0, times V1 at 0, 1. Right? So this is a well-defined closed form relationship into consecutive layers. Okay. Is that clear? Okay. Then just to warn you, the next one is the most complicated stuff. So this is the key equation in the GKR protocol that exactly defines the intuition I gave you. Basically defines the relationship between polynomial vi and polynomial vi plus 1. Okay, so it writes the multivariate polynomial vi as a sum of the polynomial vi plus 1. And in addition, we have two more polynomials, mult and add, exactly mapping to the circuit, as I said, because the relationship is denoted by the circuit. Okay? And these two polynomials, mult and add, are called varying predicates in the literature. So the input to this thing are three binary strings, G, U, and V. They are like labels of the wires in the circuit. Okay? And this mult returns 1 if and only if these three wires or three binary strings connect to the same multiplication gate. Okay? So that is the definition of this wiring predicate. Okay? And then if you plug this into the equation, you can verify that this holds. And I'm not going to show you the derivation. And if you doubt about the correctness, please ask Shafi and Yao and Guy about it. Okay, so with this equation, we can actually, the process of the Sumcheck, the GKR protocol works as following. Right? So in the first round, the server send the claim output y, which is not trusted and is marked in red on the slide. Okay. With this, the verifier is going to define a multivariate polynomial v0 and then evaluate at the random point r0. Okay. After that, the verifier is going to run a Sumcheck protocol with the prover on this equation for layer 0. Okay. And as I said, at the end of this Sumcheck, the verifier needs an oracle access to an evaluation of the multivariate polynomial inside the sum. Okay. So where does she get this oracle access? So for the part related to mult and add, she can evaluate it on her own because they only depends on the circuit, which is public. But for the part about vi plus 1, she just asks the server to send it to her directly. Okay. So up to this step, like she doesn't know, like v1 r1, v0 r0, and y can all be false, can all be wrong. But the guarantee is that as long as v1 r1 is correct, so does v0 r0 and output y. So this is a reduction.
So evaluating mult I takes the size of C time, right? I mean,
in the worst case, yes. But then if your circuit has structure, this can be done in a shorter time, sublinear time. And that's exactly why the verification time can be sublinear for structure circuits.
Right. But as you show, it's still the verifier time is linear in circuit size because just of the evaluation of mult.
Yes, yes. So this is a reduction of the correctness about output to an evaluation about the values for one layer below that. Okay. So following this idea, we can just run one sum check for every layer of the circuit like this, and eventually the verifier can reduce the claim about output to a claim about the evaluation of the input polynomial at a location chosen by the verifier. Okay. So this is the whole reduction in the GKR protocol. And finally, how do we guarantee that this last evaluation is correct? In the original protocol, it requires the verifier to store the input locally, computes this value VDRD on her own, and checks that they're equivalent. Okay? So this completes the whole reduction of correctness and guarantees that the output is correct. Okay? So that is the whole description of the GKR protocol. Is it clear at this point? Good. And GKR protocol is actually a very important protocol for this in complexity theory about efficient interactive proof for bounded depth circuits. But then the next question is, like, what is the exact Poorer complexity of the GKR protocol, right? So, like, the GKR protocol is called doubly efficient interactive proof, but doubly efficient just means that the Poorer time is polynomial time, and the verifier time is quasi-linear in the input size, right? And like polynomial time is a sweet word for like, theoreticians, but it's actually not that great if people like me want to implement it. Right? So to answer this question, we have to see what is the Poorer complexity of Sumcheck protocol, because GKR is basically running one Sumcheck per layer of the circuit. Okay? So fortunately, we have a great paper by Justin Taylor in Crypto 13 showing a very nice technique called dynamic programming to generate a proof for Sumcheck protocol if f is a multilinear polynomial. Okay, actually, it should be a multilinear extension, but I'm not going to differentiate them here. Okay. So the way it works is as following. So first, we are going to initialize an array of this multilinear polynomial f evaluated on the whole Boolean hypercube. Right? So each element is just f0, 0 goes up to f111. Okay? So this is a linear size array. With this array, the Poorer can generate the message in the first round by going through every element in this array. Okay? So it computes every element in that sum in constant time. So summing them up, overall, it takes linear time to the size of this array. Okay? And then there's a way to update this array by combining two elements into one with the random challenge received from the verifier. And the size of the array is cut by half. Okay? And then with this new array, the Poorer can generate the message in the second round, this one, again by going through all the elements in the array and generate every element inside the sum. And again, this step takes linear time to the size of the second array. Okay? And then they just do it again and again to generate all the messages, and eventually this array just shrinks to one single value. So that is the whole procedure for the Poorer to generate the proof. And the complexity is right, order of n plus n over 2 plus n over 4 and so forth, which is linear. Right? It's optimal for Sumcheck protocol on multilinear polynomials. And this technique is called dynamic programming.
So I'm still confused because at this point, still the verifier is not saving any time, right? Because again, just to compute the add I function, it's like...
this one is purely for Sumcheck. Sumcheck, the verification is login plus this oracle access to the
So you should think of the circuit as being uniform, log space uniform, in which case computing this and mult can be done very efficiently.
Oh, okay.
That's the focus, is on these uniform circuits.
Okay, so it's
Yeah, actually, that's a better way to think about it.
but also
Log space uniform, so you can generate kind of what the circuit, like which
Yeah.
gate efficiently.
Yeah. Okay.
But even in the other case, the proof size is still small. Even in the case where the
Another benefit is proof is small no matter what is the what's the structure of the circuit. Yeah. And it's not hard to see that this dynamic program technique can be generalized to like products of multilinear polynomials. We just initialize one array for each of the polynomials separately and update them separately. And when you generate proof, just multiply the corresponding elements together and return the proof. Okay, so this is a quite straightforward generalization. But unfortunately, this fancy technique cannot be applied to the GKR protocol because the equation to do Sumcheck on in the GKR protocol does not have this nice feature. Right? You can see here the multivariate polynomial inside the sum. So vi plus 1 is a multilinear polynomial. These two are both multilinear. But the annoying thing is about this mult and add. They're also multilinear, but it has a 2 times log c variables in it. Right? So if you just apply this dynamic program technique naively, the prover complexity is 2 to the power of 2 log c, which equals to quadratic on the circuit size. Right? Meaning that if you just want to lay out this array, it's already quadratic in size and time. So let alone the other things you want to do on top of that.
Why didn't it extend to general polynomials, the dynamic programming approach?
For general polynomials, I think this way of dynamic program could apply, but the time to evaluate, to initialize the array may not be in linear time. Yep. It's actually not in linear time, I guess. Yep. So multilinear is one of the important optimization proposed in Jason Taylor's paper.
Sorry, would it be, so if you have a general polynomial of degree d, would you get that your time is like n times d, or n times something that depends on d with that, or just the technique doesn't apply to all?
The technique very much exploits like Lagrange interpolation over the Boolean hypercube, which really only works for multilinear things.
Yep.
So like potentially a degree 2 thing in each variable, like everything's.
Yeah, I think you can achieve quasi-linear to explain the sparsity, which I'm going to talk about next. Okay. So this complexity is not good. And to improve this, actually in this paper, CMT12, they improved the complexity of the prover down to quasi-linear C log C by observing the sparsity of this polynomial mult and add. Right? Remember, by the definition, it's varying predicates. It returns 1 if and only if the 3 inputs connect to the same gate. So at most, in a circuit, you can at most have a C gates. So you have at most C non-zeros out of the C square possible locations, right? So because of this observation, if you think about this big array of C square size, you only have C non-zeros. So you can index it in a different way to make it linear. But the problem is that if you do that, there's no guarantee that after update, your size of the array will shrink by half. Right? Because there's no guarantee that 2 non-zeros will always combine to 1, right? So the size of the array is always linear, is always C in all rounds. So the complexity is C times log C using this approach. Okay? And after that, people have spent great effort trying to optimize this prover time. And the way is to exploit actual structure inside the circuits. Okay? So in Taylor 13, he showed that if the circuit is regular, for example, matrix multiplication and the multiplication tree, we can make it linear time. And then if the circuit is data parallel, we can bring down the complexity to C times log C prime, where C prime is the size of the small circuit repeating multiple times. And then later, this is improved to nearly linear, C plus C prime log C prime in this paper by Wabi et al. In 2017. And in one of our previous work, as a side product, we show that even if the copies are different, we can still do this C log C prime. Okay?
What's C prime again?
It's the size of the small circuit repeating multiple times. They are parallel fashion. Okay. And finally, in this year, in our paper, we managed to come up with a new algorithm to generate proof in strictly linear time for arbitrary layered arithmetic circuits without assuming any structure in the circuit. Okay? So this.
The layer restriction, what exactly does it mean?
Well, just follow the original GKR protocol. You run one sum check for every layer of the circuits. So.
What does this mean in practice, the restriction of layers?
Well, in principle, you can have connections between layers, but if you just do some relay gates, in practice, it should be fine. I don't see any layers I don't see any practical circuits that is not layered. But in theory, changing an arbitrary circuit to layer circuit, I think will incur a quadratic overhead or something. Yeah. So that's why the claim is only on layer circuit. Okay. And this subsumes all the previous variants of the GKR protocol. Okay. So then how do we do this? I guess the key is to look at this equation for long enough time. And after several years, things start getting blurred, and you realize this thing can be decomposed in the following way. Okay.
What does the prover know about mult and add?
What does it all the information? Yeah, there's the circuits.
How are they represented for the prover to run?
Well, think about the prover has access to this circuit.
So does it have local access, kind of?
Yeah, the orange. What?
I think when you do this, do you think it takes one, a single step to compute mult and add? That's what you're asking, right?
Actually, no.
So can you do transform, you were saying with the holographic proofs yesterday?
No, there's no preprocessing like that. Just think about it, just access to the original circuit.
Right. So
Literally original circuit.
Yeah.
So if the prover has every gate written down with the wires going into that gate.
Yeah.
He can run this protocol in linear time in the size of the circuit.
Very nice. Thank you.
So the way is to decompose this whole sum check into two phases. So for simplicity, let's focus on the part with mult, because the add part is just a similar case like this, and you can just do the same trick. Okay. So this sum can be decomposed into two phases. In the first phase, we are going to sum on the first variable, or first vector of variable u. Okay. And then this sum can be expressed as the sum of u of this polynomial h times polynomial vi plus 1 u, where h is given by this ugly form of sum. Okay. And turns out both of this polynomial h and vi plus 1 are multilinear. So if we can have a way to initialize them on the Boolean hypercube, we can actually apply the dynamic programming technique in Justin Taylor's paper and complete this step in linear time. Okay? So actually that is the contribution we make. So we figure out a way to compute this whole complicated thing from h000 up to h11 in linear time by a linear scan of the circuit on this level. Okay? And unfortunately, I'm not able to present the whole algorithm given the background knowledge here, but this is the idea. Given a linear scan, initialize h on the Boolean hypercube. And after that, we just run the dynamic programming technique on the product of two multilinear polynomials and get the proof in linear time. Okay? And this vi plus 1 u is the easy part because the evaluation initialization is just the values in the circuit.
And this will work for any sparse polynomial, or it's something special?
Yeah, just any sparse polynomial. Yes, it can be generalized. Yeah. And then after the first phase, the equation becomes something like this. So the variable u is already bounded to a random challenge by the verifier. We call it R of u here. So in this equation, we are summing on v only, and then this vi plus 1 ru is merely one value, a single number, which is computed by the prover in the previous phase. Okay? Again, so this is a product of two multilinear polynomials, and we can just apply the same trick. But turns out, initializing this one is not for free. We have to go through the original, a similar approach to compute it on 00 up to 11 by another linear scan of the circuit from scratch. Okay? And after that, we're just going to apply the dynamic programming technique on this one to finish the second phase. So that is the picture of the whole linear time protocol. Okay, so in sum, we divide it into two phases. In each phase, there's a linear time to initialize and linear time to run dynamic programming. So overall, the prover time is linear. And also, as you mentioned, this can be generalized to anything of this form divided into constant number of phases as long as the polynomial in each phase is sparse if it has more than linear terms. Okay? And this generalization actually can be nicely applied to the original equation in the GKR protocol, where you have an identity function, identity polynomial. You call it beta in the original construction. Okay? So to end this part, this is the evaluation for our protocol, comparing to all the variants of existing ones on different types of circuits. And that, as you can see, for regular circuits and data parallel circuits, the performance is comparable to those protocols working only for those type of circuits. And if the circuit is like a random, then we have a big improvement on the running time. So this means that we can just implement our version, and this subsumes all existing ways of running the prover. Yeah.
We're looking at the prover time and just the interactive proof, not the IPCP variant. Right? We're just looking at
yes, only the GKR part. Yeah. Another improvements I want to highlight is after you only have one version that works for arbitrary circuits, this gives a very nice interface that can take arbitrary layer circuits. And this is very important if you ever try to implement GKR protocol. It's really a nightmare to represent your circuit as a data parallel one per layer, right? So now you don't have to worry about that, at least for the efficient prover time. You can just write it as a layered arithmetic circuit, and this could be compiled from like high-level languages. Okay. So we're good with the GKR linear time. So up to this point, let's look at the properties of the GKR protocol, right? The good thing is the proof size is succinct, no matter what's your circuit, right? So it's D times log C. And the verification is also succinct if the circuit has structure, so-called log space uniform. Then the verification time is D times log C plus some work on the input. And the prover time is very fast, asymptotically optimal, concretely only additions and multiplications in the finite field. Okay? But it's actually not quite a proof or an argument system, right? It does not allow the prover to have witness, right? You see this model looks like a little bit different from.
If you want the log space uniform circuit result, there's another sub-protocol.
Yeah, exactly. Right? So yeah, when we talk about asymptotics, I refer to log space uniform. When we talk about concrete things,
you preserve the linear time for that part as well, because
this is another GKR protocol, right? And that's
GKR protocol, and it doesn't matter what it is, and so everything works out, and you actually get linear everything.
In theory, yes, I think. But we didn't implement the recursive one for concrete circuits. For concrete ones, it just we view it as data parallel or just the concrete numbers.
Okay.
Right. Yeah, and then going back, it does not allow the prover to have witness because in the last step of the GKR protocol, the verifier has to compute this VDRD on her own to finish the reduction. So this requires the verifier to access all the inputs to compute it, so it does not allow the prover to have witness. Okay? And also, this protocol is not zero knowledge, which I'm going to explain next. So to turn the GKR protocol into an argument system, in one of our earlier work, we actually proposed a way using polynomial commitments. Okay? So the way works as following. So this is a paper in 2017. So we allow the prover to have a witness, but the prover is going to define a polynomial using the witness, which is the multilinear extension of the witness, and commit to it using a polynomial commitment scheme. Okay? After that, the verifier and the prover are going to run a GKR protocol. At the end of this protocol, the verifier will receive a claim about VD-RD by the prover. And to
Say what you mean by polynomial commitment scheme?
It means that you can commit to a polynomial and open to an evaluation point later. And it should be succinct. The commitment is the constant size. The opening, the proof size and verification time should be logarithm to preserve the original complexity of GKR.
Sorry. So you commit to polynomial. How long does it take to commit? Because you can always commit to polynomial by just committing to all the.
Yeah, it takes linear time to commit, but I want the commitment to be small, a constant size.
But linear time in what? Sorry.
Linear time in the size of the witness.
Okay, so just linear in the size of the. So it's
Yes.
much smaller than just committing to each value. I mean, the trivial way to you can just commit to each value of the polynomial, right?
Yeah, the prover time is fine in that case. but the commitment is linear size.
Do a hash tree on it, so you get choice.
But then how do you open the polynomial at the evaluation point?
Right, so I'm saying you can just commit to P of 1, P of 2, P
But
of 3.
maybe then the values are, there are a lot of values, right?
Exactly. So it's not efficient for the prover.
Yeah,
So
but-
you do it
yeah.
efficiently in the prover, that's only depends on the witness. That's kind of the point.
So it's a commitment to the formula of the polynomial, but not to all the values, right?
Exactly.
Right.
Exactly.
And then at the end, to validate that claim, you just open this commitment at that particular point that completes the reduction and guarantees that the output is correct without sending the witness directly back to the prover. So this is an argument system for building on top of GKR. Okay? So that's great. That's the previous work, but this is not zero knowledge. Okay? To see why is that, the GKR proof is actually leaking information. Okay? So these univariate polynomials sent by the prover, you can think about it as the weighted sum of the coefficients of this f. Right? The weighted sum is on the random challenges chosen by the verifier. Okay? And then in GKR, this f is defined by, for example, the values in the circuit. So you can think about these messages as weighted sums of the values in your circuit, which means it's not zero knowledge. Think about the case your circuits are all zero, then I'm sure that these proofs will be all zero, or some part of them will be all zero. So this is leaking information. Okay? But yeah, weighted sums. And then how to turn it into zero knowledge. In prior work, in two of the prior works, we actually take the Kramer-Damgard transformation to put everything in the commitments. So instead of sending these messages in plain text, we're going to embed them into homomorphic commitments. Okay, so these are in one of our previous work and another concurrent work by Wabi et al. Okay? And then instead of just testing on the plain text, we are just going to test on the commitment. Every time you want to add or multiply by a constant, you do it homomorphically in the commitment. Every time you want to test equality, you just run a sigma protocol for equality test, zero knowledge equality test. Okay? So in that way, you only learn that test goes through, but not any information. But this approach introduces a very high overhead on the verification time. Right? This is because every addition becomes a multiplication, every multiplication becomes an exponentiation, and every equality test becomes a sigma protocol for zero knowledge equality test. Right? So this is bad in practice. Okay? So instead, we are taking a totally different approach, and the approach is called masking polynomial. Okay? And the idea was originally proposed by Chiesa et al. In their 2017 paper. Okay? So the idea is, instead of running Sumcheck on this original multivariate polynomial, we are going to run it. We are going to construct a random polynomial delta, and do a random linear combination and run Sumcheck on the whole thing. Okay? And then by the linearity of Sumcheck, everything still works out. And for security reason, you need to commit to this random masking polynomial and open it using the polynomial commitment at the end of Sumcheck. Okay? Yeah, that's the idea. But then in the original paper, they just use a random polynomial that is of the same size as the original polynomial. And because of that, the commitments and opening is not very efficient in practice. So in our paper, we show that it suffices to mask with a very small random polynomials in order to achieve zero knowledge. And the idea is actually quite simple, because Sumcheck is leaking information, but the proof size is only log of c, logarithmic size on the polynomial, right? So it cannot leak like all the information, like all the coefficients of this polynomial. At most, it can leak like the entropy of log c numbers. That means it should suffice to mask this thing with that many random coefficients, right?
So who chooses this delta? What is this delta?
The prover chooses it.
And he gives it to the, so.
It commits to it, and just the verifier does a random linear combination. Yes. So we just follow this idea and derive everything out, and turns out delta can be chosen in this nice form. It's just the sum of univariate polynomials, which maps exactly to the messages of the Sumcheck protocol. And because of this, whatever you do on top of this thing, committing to it, opening to it, introduce no overhead because it's only logarithmic size. Okay. So this is the high-level idea, and also thanks Ali to about this idea during our discussion.
Yeah. Like a general way that often works for achieving zero knowledge is to just add some random dummy values that do not affect the output. Is this approach problematic for GKR style protocol?
No, this is actually the thing to mask it.
But presenting it at the circuit level, kind of like pre-compiling the circuit into a slightly bigger circuit that has some random dummy values.
That one I haven't thought about it, but maybe we will introduce some overhead to the prover time, at least linear to the circuit size. This way is basically introduce no overhead. It's an additive logarithm overhead, so it's just nothing in practice. Yeah. And also there's some, yeah.
Question about the previous approach with the zero knowledge equality test. Can you somehow batch them to do kind of the
yes, you may save some constant factor, but I'm not aware how to save the symptotics. Yeah.
So that will truly mask your polynomial. There are no mixed terms, right?
Yeah, there's no mixed terms.
So how does that mask? Doesn't
No, you don't have to mask every coefficient. As I said, the proof is only log. I'm sending you log C weighted sum out of C things, so you cannot leak everything, right? You cannot reconstruct the original things. That's right. Otherwise, you have a super efficient way for transmission. Okay. So I guess I'm running out of time, and very quickly going through the last one. Okay. So as I said, there's a nice way to turn it into an argument system, but the original polynomial commitment we're using is based on bilinear maps. That was introduced by Papamental et al. At 2013, which is a generalization of Cate's polynomial commitment to multivariate case. Okay. Because of this polynomial commitment has a trusted setup phase, and is also based on knowledge assumption. Everything is the same as snarks. So how to remove it? We need a transparent polynomial commitment scheme without trusted setup phase. And this is actually on the wish list of Ria's Christmas thing. Yeah, and here's a gift for his Christmas. Okay. So the first attempt is, how about we just use the general purpose zero knowledge proof without trusted setup? Right? Polynomial commitment or polynomial evaluation is just a special function. How about we just use any general purpose thing like Ligero, Stark, Aurora, bulletproof, or anything? Then that satisfies the requirement, right? It's a transparent polynomial scheme implemented, for example, as a circuit. But in those schemes, the verification time is linear to the size of the circuit because they are general purpose, and in the worst case, you have to read the entire circuits. That's why it's a linear time verification if there's no preprocessing. Okay? But that's not the case for polynomial commitments, because polynomial commitments is a well-structured computation. So the way we do it is by viewing polynomial evaluation as an inner product between the coefficients and the monomials generated by the evaluation. So here is a univariate case, but it's just very straightforward to generalize it to a multivariate case. You take log n inputs as A and then expand it to a linear size vector, all the monomial evaluations. Okay? And these coefficients are witness, known only to the prover, and this whole vector on the input is public, known both to verifier and the prover. In the first step, we are going to develop an inner product protocol based on general purpose ZKP. This is a little bit non-black box way, but you can still think it as just black box use. And we are using Aurora. Okay? But as I said, the sad thing is the verification is running in linear time. Actually, the one we are using runs in quasi-linear time, just for some simple issues. But if you zoom into this verification algorithm, what is this verification doing, right? It expands A to the vector of A. And then if you still remember, Nick's talk yesterday is doing some resolvent code encoding using inverse FFT and then evaluate at the random points using FFT, but these are not important. Just expand to A, do 2 FFTs. So this is the verification algorithm, right? But if you look at it, you realize this verification algorithm takes a small input A, logarithm size, and the depth is log n because of FFT, and it's very uniform circuits. So how about we just delegate this thing to the prover and verify it faster than computing it? So do we have a protocol that works for small inputs, low depth circuits, and uniform circuits, right? It's just GKR itself. So we just delegate this whole thing using GKR again to the prover side, and the complexity to validate it is actually only logarithm on the size of the circuit. Okay? So this gives a new polynomial commitment scheme without any setup. Everything here in black are the same as Aurora. It's proof size log n square, prover time log n, symmetric key, random oracle, fast and plausibly equals quantum secure, and the only improvement is on the verification side. It's log n square.
What sense does it go with the depth?
anymore?
This is only for the polynomial commitment, and that's exactly on the next slide. So putting these together, we get a new transparent ZKP system named Virgo. The proof time is linear plus a log n on the witness size, where n is the size of witness. Proof size is d log c plus log n square. Verification time is the same if the circuit is log space uniform or structured in practice. Okay, so I will end the talk with just some numbers of the performance. So I guess this table is quite dangerous to show because we get complaints all around the world after we post it. So if you think your system should run faster, just send me your favorite number and I will update the table. Okay. But from this ever-changing table, we can still conclude something. That's exactly the thing I said at the beginning, right? Using this thing based on GKR, the proof time is very fast because it's strictly linear to the circuit and only additions and modifications for the main body. And we still need FFT for the polynomial commitment part, but that's only on the size of the witness. Okay, and there's no way you can optimize exponentiation to be faster than multiplication, right? So, and then the verification is succinct if your circuit has structures in it. So that's all of my talk, and thank you.
Maybe one quick question while Daniel sets up.
Well, I have one. Somebody has. So when using the variant of PST, you are using knowledge assumptions on that variant to get the committed polynomial back.
Yes, yes.
Using the Aurora-based variant, how are you proving it in the random oracle model? What are you?
You just in the random oracle for knowledge, like proof of knowledge. Yes, yes. This is the same thing as in the Aurora paper. Yeah, and we don't know, like we haven't thought about how to, if you can do it better with better assumptions. Yeah.
Yeah.